All right, good morning. Uh, Today we continue with the electromagnetic induction. We talked about that how we can generate a current through the moving magnetic field. In the previous chapter we learned that the moving charge, which is an electric current, can produce a magnetic field. In this chapter, the focus is how we can produce an electric current by moving the magnetic field. So there are a few things we learned here called the electromagnetic induction phenomena. One of them is we have changing magnetic field where we have two conducting coils. One is connected through the battery, and when we turn the switch on, the current flows through the coil. As a result, the magnetic field will change, will be produced, and it will change through the coil, and this magnetic field is going to affect the pass through the coil, which is not connected to the to the battery. So as a result, the changing magnetic field will produce a current, and that current can be seen using the galvanometer. Now, this current will be there momentarily. As the current flows through the coil, the magnetic field is generated, and the field will be constant after a while, and there will be no more current. After that, this galvanometer will show you the zero readings. We also noticed that moving a magnetic charge, the magnetic bar in a conducting coil which is not connected to the battery will also induce the electric current. And if I move this magnet through this coil which is not connected to the battery, the current will be generated. So as long as you are pulling or pushing the magnet through the coil, the current will be keep induced through the coil, and which can be seen through the galvanometer. Now, if we stop moving the magnet, which means there will be magnetic field will be constant over there, because magnet is there, the magnetic field has to be there, but the magnetic field is constant. It's not changing anymore. So as a result, there will be no more current in the induced current in the conducting coil. The third thing which we noticed is we have a permanent magnet, and we bring a conducting coil which is connected with the galvanometer, no battery source. If I move the conducting coil, as a result, there will be a induced current produced in this conducting coil, which can be noticed through the galvanometer. So as long as I am keep pulling or pushing this coil through this permanent magnet, the magnetic field will be there. So it means there is a change in the magnetic field line is important for the magnetic field to be produced. Now, here let's try to find out the direction of the induced current. Now here, if I look at this picture on this left hand side, so in the top picture, what I see is the magnet is moving towards the conducting coil. So this V is the velocity of the motion of the magnet. As the magnet goes towards the coil, the magnetic field lines will be changing through the conducting coil, and this is an external magnetic field, just to label it, because it's an external magnet. Now, the direction of the induced current can be measured, of course, with the galvanometer, but keep in mind, if I look at the lower picture on the left hand side, here the same magnet moving towards the coil, conducting coil, but at the same time the current is induced and we have another magnetic field produced through the coil. Keep in mind, we learned that whenever there is a current carrying wire, carrying a current, the current flows through the wire, there will be always a magnetic field produced around the wire, and that magnetic field can be seen with using the right hand rule. Right hand in such a way that if I grasp the current carrying wire in my right hand with the thumb pointing to the direction of the current, and the curved finger will point to the direction of the magnetic field, which is an induced magnetic field. There are two things we are talking about: the external magnetic field, which is due to this magnet, and then here is an induced magnetic field. Now, if we look at this, the direction of the external magnetic field is towards right, whereas the direction of the induced magnetic field is towards left. And if I follow my right hand by grasping this coil in such a way that thumb points in the direction of the induced current, the curved finger will tell me where the magnetic field, induced magnetic field, will go. Now, here the induced magnetic field is opposing the increasing external magnetic field. That's an important point, that the external magnetic field, when it's moving through the external magnet towards the coil, as I am moving close towards the coil, I am increasing the magnetic field, external magnetic field. Now, the induced magnetic field, due to the induced current, using the right hand, by grasping in such a way, the thumb points in the direction of the current and the curved fingers to the direction of the induced magnetic field. So the induced magnetic field is opposing the increasing external magnetic field. Now let's do the same thing in this picture on the right hand side, on the right hand column. So here I have this magnet, external magnet. Instead of moving towards the coil, I am pulling it out of the coil, away from the coil. So it means that when I do that, the external magnetic field will decrease. Alright? Now if that happens, the direction of the induced, since I change the magnetic flux, I change the direction of the external magnetic field lines. Instead of going inward, now they are going outward. As a result, the direction of the induced current will also change. And if you can notice, this direction of the induced current over here is opposite. Now, if I follow that, the direction of the induced current will grasp this coil in the right hand, the thumb pointing to the direction of the current, and the curved fingers will tell you the direction of the induced magnetic field. Now, my magnetic field, external magnetic field is decreasing. I am pulling out the external magnet, whereas my induced magnetic field is opposing that change, right? It is in the same direction as the decreasing magnetic field. All right? So this is opposing. So what it means? It means the induced magnetic field, no matter what is the direction, no matter whichever way you move your external magnet, no matter whichever way the induced current is, of course that induced current is relative to the motion of the external magnetic field, changing external magnetic field. The induced magnetic field will always try to keep the magnetic flux through the coil area as a constant. Here, when I was increasing the external magnetic field, the induced magnetic field will oppose this, try to keep the constant magnetic flux through the coil so that the current keep moving. Now here, when I am pulling this magnet out, as a result, I am decreasing the external magnetic field. So in order to compensate that, the induced magnetic field will go in the same direction where the magnetic field due to the external magnetic magnet has the direction of the external magnetic field is. So as a result, since we are pulling it out, the magnetic field lines are decreasing. So as a result, the induced magnetic field will try to compensate this effect and try to keep this magnetic flux through the coil area as a constant. Having said that, so here is another example one can look at. So here I have a magnet, and this is a conducting coil. Now the magnet has a south end towards the coil and the north end towards the opposite direction. Now I move the south end towards the coil, so though it means the magnetic field line looks like coming out of the coil. So as a result, the current will be induced through the coil. Now if you follow this current, so it means, as I said, the magnetic field lines are going out of the coil because the south end of the external magnet. And induced magnetic field will be opposing this change again. It will be opposite to the external magnetic field lines. So this will be something like this. If I have this bar magnet which has a north and a south pole, this is the velocity of the motion, and this is the conducting coil. So the current, now the magnetic field lines are something like this, right? So they are going towards it, towards the south pole, right? That is the magnetic field due to the external magnet. Now if the current flows through it, so the direction of the current will be such a way that the induced current, if I grasp it in my hand, then the induced current will be in this direction, which has to oppose the external magnetic field, which is the cause of the induced current. So, as I said, so this process, all it is about keeping the magnetic flux through the coil constant, right? So we can also look at it in another way over here. So here again, now the same magnet, so the magnetic field line, as I said, they are going out away from the coil because I have the south end of the magnet towards the coil. So the magnetic field lines due to the external magnet going out of the coil. As a result, the induced current, see, the induced current will produce a magnetic field which will be opposing this external magnetic field. Now, no matter what, whether you move the magnet or you move the coil, it doesn't matter. In both ways, this is a relative motion, so in both ways you will have the induced magnetic field produced, and that induced magnetic field will oppose the external magnetic direction of the external magnetic field. If the external magnetic field is increasing in the coil, so that will be opposite. The induced magnetic field will be opposite to that, so that it will try to compensate the constant, keep the flux through the coil the constant. Now keep the same flux basically through the coil. Now in this case, so the magnetic field line due to the external magnet, let's say in this case the coil is moving. This is the velocity v of the coil. Now coil is going towards the external magnet. So the magnetic field lines looks like due to the external magnet going out of the coil. So as a result, the flux is changing, right? The change in flux will produce an induced current in the coil, and this induced current will generate an induced magnetic field. As we learned earlier, whenever there is a current flowing through the conducting wire, there will be always a magnetic field around it due to the flow of the charge. So this magnetic field will be opposing the induced magnetic field will be, so it will be like this. The induced magnetic field so here is the induced magnetic field. Alright, so this is opposing the external magnetic field. So in order to keep the same flux through the conducting coil. So this way we can set up a current in the conducting loop, loop. Now this leads us to some important fact which is called the Lenz's law. So what does the Lenz's law says? So this is very important. You have to be careful about this Lenz's law. It only tells you the one thing about the direction of the induced magnetic field, and that is very important part, because this is what I just mentioned. So the direction, it says the direction of the induced current in a coil such that it's B induced. Induced magnetic field opposes the change in the magnetic flux. Opposes the change in the magnetic flux through the coil's area produced by the other object, whatever the object is. Now, if the magnetic flux through the coil is increasing, the direction of the induced magnetic field, if flux is increasing, the magnetic field direction is such a way it will decrease, will try to decrease in the flux. If the magnetic flux through the coil is decreasing due to the external magnetic field, this magnetic field flux will be due to the external magnetic field. And this magnetic field flux will also be due to the external magnetic field. So the induced magnetic field, which is due to the induced current, will increase the flux. Here, if the magnetic flux due to the external magnetic field is decreasing in a direction of the induced current, then the induced magnetic field will lead to the increase in the flux. So in conclusion, what we can say, the direction of any magnetic induction effect or magnetic induction effect is such a way that it has to oppose the cause of the effect. And if you look at this picture, here is a conducting coil. Now I have an external magnetic field which is with this dark blue line arrow. Now here what is going on is I am changing the magnetic field due to an external magnet. It's the change is this much. This is the light blue color. Now, due to this change, the magnetic field lines and the flux changes. As the flux changes, the EMF, the current is induced in the coil. As the current is induced, there is EMF. Of course, something is there to move the charges, that is the EMF. Now, which is the voltage basically. So, as the current is induced, it has to induce the magnetic field. And this is the induced magnetic field. And you can see the size of the induced magnetic field. It will be equal to the change in the magnetic flux by the external magnetic field. So here the change in the magnetic flux is the light blue color arrow. So this induced magnetic field will be approximately of the same size. It's not exactly same, looks like over here, but this should be approximately of the same size. So it is opposing the cause, right? This induced magnetic field is opposing the cause, and the cause is the exchange in the external magnetic field through the coil. So this change in magnetic field, which is the cause, is opposed by the induced magnetic field, which is produced by the induced current through the coil. All right, this is the Lenz's law, and this is very important, and this has a very large implications, of course, and this opposing the cause, which is by the induced magnetic field, told to us by Lenz, and in the form of the Lenz's law, which will introduce a negative sign as we go further. I will show you. Now let's talk about a little bit of the implications of that, which is in the form of the eddy currents, which is an implication of the Lenz's law. Now I have a conducting plate instead of a conducting coil. I have a conducting plate. All right. Now this is placed in between a permanent magnet. As you can see, the north pole and the south pole, the magnetic field lines go from north to south. Now if I move the conducting plate with the force, which is the F pull, this is the force of my hand, okay? If I pull this, as a result, what is going to happen is there will be a current loops produced over here. So the current will start with charges will start moving in the form of the loops, that is similar to the whirlpool in the moving water, like this. Okay, so that the currents will start flowing in the form of the whirlpools. And if I look at that, now the Lenz's law tells us that the effect will oppose the cause. Now the cause was, what is the cause over here? The cause is my force, which is the pull force for this. If I pull this conducting plate, which is the pull force. Now the moment I pull this, there will be an effect of this cause, which will also be a force, apples to apples, oranges to oranges, right? So if it was a magnetic field changing, there will be an effect of the cause of the magnetic field will be a magnetic field, which is the induced magnetic field. But now, since we are talking about the force, which is the pull force, so the effect will be, there will be opposite pull force. So on each whirlpool, on each loop, there will be a force, and the size of the force combined together will be equal to this force, my pull force. So this is the cause, and the effect is that. So the effect will oppose the cause. So that is what the Lenz's law tells us. Now one can also see over here. So this is the conducting plate, which is with the blue color or purple color, and this north pole should be with the blue color in principle. So it turns out to be weird. Let me write it here: blue, and this conducting plate, let's call this purple. Okay. Now here is my pull force. Now due to my pull force, there will be a force on the other side. So keep in mind, magnetic field, when I pull the conducting plate, I change the magnetic field. Although there is a permanent magnet, but I am changing the how many field lines are passing through the conducting plate. So I am changing them. As a result, I will have an induced magnetic field, which will be opposing this cause, right? This change in magnetic field, and here is my pull force, and I have another force over here, which you can see with these red arrows on the top figure, and that is opposing my pull force. All right. So red arrows on the plate, these are the opposing force. All right. Due to the, now this force is between the external magnetic field and the induced magnetic field. All right, the induced magnetic field due to the induced current in the loop. Now this has very important implications. One of them, I'm sure you might have seen this. This big giant drop rides. Sometimes might be scary too, right? So one of these is in the Dream World in Australia. So what happens over here, due to this eddy currents, we use this effect in order to use the magnetic brakes. Okay? So the advantage of these magnetic brakes is there is no wear and tear onto by applying the physical brakes over here. Okay, if we have the physical brakes to stop this drop ride, then it means there will be a wear and tear, right, of the parts. So these magnetic brakes, so we will have an induced current, and due to the eddy current, just the same process as the eddy currents. I pull the conducting sheet from the magnetic field, so there is a magnetic field in there, and you change the flux through that. By changing the flux, we produce an induced magnetic field, and as a result, this induced magnetic field will oppose the cause which produces it. So it means the external magnetic field and that induced magnetic field, they will oppose each other, and the same way the pull force, which is the gravity over here, that will be opposed by a magnetic force due to the induced magnetic field, and they will be opposing each other. As a result, that will be magnetic brakes, as you can see here. So inward magnetic field, and then there is a force which will try to stop this drop ride. Now, not only that, as I mentioned in the beginning of this chapter, that how do we use the vending machines. Of course, we use the vending machines to get some food, but how the vending machine knows what coins you put and where these coins go and how does this count. So there are different bins of different coins in the vending machine. So what happens is the eddy currents are used to recognize these coins, okay, during the damping motion. So what happens is the magnetic braking is used for the coin sorter. For example, if I roll the coin on the track into the vending machine, there is a magnetic flux produced in the vending machine. There is a system. So when I roll the coin, so that will there will be a magnetic field. As a result, there will be an eddy currents produced, inducing eddy currents like this, and this will slow down because when I push the coin into the track, I applied a force. Due to the eddy currents, there will be an opposing force over there, which will be due to the induced magnetic field and the induced currents. So that opposing force will slow each coin to a speed that is based on the coin's metal type and the size of the coin. Then, when it slows down, the coin exits the field region with the different speeds. Each coin will exit the field region with the different speeds, and it will fly like a projectile, and the distance is already calculated, and the bins are placed for each coin. The different bins are placed over there, and the coins will fly like a projectile and will land into the corresponding bin. And when the coin drops in the corresponding bin, then the bin will trigger that, okay, there is an extra coin came, 1, 2, 3, or whatever. That counts how much money you put. And so as a result, you will see that will trigger the vending machine that say what is the amount of money put into it and what you want to get out of that. All right, now let's come to the next step, and our friend Mr. Hans Oster, he discovered that an electric current produces a magnetic field, which we saw in the current carrying wire. I has a magnetic field around it, right, which is induced magnetic field. It's a straight wire. Of course, you can have the circular wires. Now, the question was, if we started this chapter, the question that is the opposite true? Can the magnetic field create an electric current? And sure enough, in 1831, Mr. Faraday and Henry showed a changing magnetic field can induce the electric current in the circuit, and that leads to Mr. Faraday to come up with the Faraday's laws. Mr. Michael Faraday, who is not only came up with this Faraday's laws, but he is an inventor of the electric motor, which we discussed in the previous chapter, and also the generator generates the electric current. We will talk about that in this chapter soon. And then also the inventor of the transformer. We will also talk about that. What does the transformer do? It's your chargers for your smartphones. They have the the transformers, because when you plug in your charger into this wall socket, so over there you get 120 volts, but your smartphones do not need 120 volts. Even your computers do not need 120 volts. With this 120 volts, they will be fried. So what happens is there is a transformer which slows down the voltage. We will talk about that. And then he will come up with the electromagnetic induction. So let's see, what does the Mr. Faraday says. So here, in order to understand that, let's say we have a single circular loop with the zero resistance. There is no such thing called a zero resistance in the real world. But we have an ideal loop which have a zero resistance from here to here, and then we put a 100 ohm resistor at the end between to join the two ends of this coil to make a circular coil. Now between the two poles. Now this whole system is placed in between the two magnetic poles. This is the external magnetic field. Now here is the north pole and the south pole. The external magnetic field lines go from the north to the south. Now the current, which can be measured through the galvanometer, and when I move this coil, the induced current in this system is 0.01 amp, which can be measured, as I said, with the device ampere meter. And now, what is the voltage induced? Let's look into that. So, since we wanted to see the voltage by the induced current, which is the EMF induced, so we put an external resistor so that we can find out what is the voltage drop across here, and we also said that this is an ideal loop except for this external resistor. Now using the Ohm's law, which we learned previously, V is equal to IR, the current is 0.010, the resistor is 100 ohms, so we got 1 volt of the. Now let's see, if we do this, have a plot this thing in the form of the we've plot this in the current and versus time, and then we see the flux versus time. So if we look at this, the flux is magnetic field times the area, right? When I move this coil, so there is a change, there is a magnetic field which is applied by the magnet, and then the area of the coil, which is through which the magnetic field line moves. So the flux is equal to B dot A So the magnetic flux B dot A, B and Ln B times A cosine of the angle between the area vector and the normal to the area vector to this coil, right? The normal to the area vector to this coil is like this, and then the magnetic field lines, so that will be the flux. Now, of course, this flux changes from initial value to the final value. Let's say to start with it was 1 Weber, and then goes to the final value. So now, if I plot this flux as a function of time and see the flux initially to start with, when the magnetic field line passes through the coil, all of a sudden I have a lot of flux change, right? So at the beginning it was 3 Weber, and then it slowly started coming down with time, and at that time t was 0 seconds, and after some time 2 seconds the flux came down to 1 second because it's slowly settling down. As long as you don't move, the flux will generate immediately as the field line passing through the conducting coil, and then if you don't change anything, this flux will start coming down and the magnetic field line will not be changing anymore, right? So then if I draw the slope to this, basically this is the slope, so that slope which is telling me the external decrease in the external magnetic field, alright? So this is the decrease in the external magnetic field. And then finally it becomes constant. At this point there is no current. So as the magnetic field is changing, you see there is a current in the circuit, and this current goes and stays constant. When the magnetic field becomes constant, the current will drop immediately. And then there will be, as the magnetic field is constant, no current. Alright? So what is the change in the flux? This is from the final value, which is 1 Weber, and the initial value, which was 3 Weber. So final minus initial. So this is the final flux minus the initial flux. This is the change in flux, which is equal to 1 minus 3. This is negative 2 Tesla. Tesla times meter square. Okay. Now the time it took is from 0 to 2 seconds. So this will be, final time is 2, initial is 0, right? So this is equal to 2 seconds. So how much is the flux change in a given time? That change in flux with a given time is equal to negative 2 over here divided by 2 will give me the negative 1 volts. And look at that. Using the Ohm's law, I got it 1 volt. And using the change in flux, I got 1 volt. Now, this negative sign tells you the direction, okay? That positive or negative. That depends on the current. But, so in magnitude, you see, if I put this resistor, just wanted to make sure the confirmation. From the Ohm's law, I got 1 volt current. And from here, I draw this, I plotted this through the plot between flux versus time. So as a result, I got the change in flux is with respect to time. This is equal to 1 volt, and this is nothing but the EMF. So, all right. Now, what is the result of this experiment? So this is an experiment which tells us some important results, and it says a current is set up in the circuit, right, that is relative to the motion of the magnet and the loop, right? Whether you move the loop or you move the magnetic field, you change the magnetic field lines, so the flux changes. So now, whether we change, as I said, the loop or the magnet, we see that there is a current induced. Now this is induced current, and with the induced current we have seen the voltage is there, and that's called the induced voltage and called induced EMF. Now let's put everything together. Now as I said, the Faraday's law says induced EMF is equal to the change in flux with respect to time. Now it means the induced EMF in a circuit equals to the rate of change of the magnetic flux through the circuit. Alright? Now this has been put over there. Now I put the modulus, which is the absolute value. We don't talk about the negative sign yet. And if I put the number n over here, this n corresponds to the number of turns in the loop. How many turns in the loop are there? So in this case, for example, if n is equal to 1, so there is the one loop. If there are more than one loop, that is the number n. If there is nothing, then it's a 1, right? It should be mentioned in the problem. Now, what is the flux? Flux is B times A cosine of theta. So if I do that, the flux is B times A times cosine theta. Now, this is the EMF induced. Now we are connecting the flux with the magnetic field and the area. Now again here, whether the magnetic field change or the area change, this delta is the change. Delta means the change. Delta represents the change. So whether the flux change or the area of the coil change, when you pull or push the coil through the permanent magnet, it means you are changing the area through which the magnetic field lines are going through. Or if you move the magnet, it means you are changing the magnetic lines. So no matter what you change, the EMF will be induced over here. Now, here is another thing. One can look at it, the Lenz's law. This is the implication to the. Now we combine both Faraday's and the Lenz's law. Okay? So what the Lenz's law says? So here is the change in the So here is I have a magnet coming towards the coil. So this is the coil, right? This circle. So the magnetic field line, which is shown with the red arrow, it's coming. It means now it's changing, right? So when I am dropping this, I am changing the magnetic field. So first it was still, and then I start moving, and it's changing, right? From here to here. Now the total length is this, the red arrow. Now there is a change in the magnetic field. Now how much is the change? If you look at this, so the change is this, right? In order to compensate that, to keep the flux constant, right? So the EMF is induced, current is induced, so the induced current will have, if you look at it the right hand, so the induced current is here. Due to the induced current, the induced magnetic field is here, right? So this induced magnetic field is equal to the change in the magnetic field. Alright? Now, instead of that, let's start pulling out this magnet, the external magnetic field. Alright? This is the B external. Right? So now I started pulling it out. So the B external, originally it was like this with the light color arrow coming down. Now it's going back. So when it goes back, it reaches to this point, the red arrow. Now it means this much is the change. Now if this is the change, now the induced current will be in this direction, will be opposite. Now if the induced current will be opposite, so it means the induced current is here. Now I take this induced current, and then the induced magnetic field over here is inside B induced, and the same way over here. So the induced magnetic field over here is inside, right? If I use my right hand, thumb points in the direction of the current, and curl finger will tell you direction of the magnetic field. If on this side, outside of the loop, it's going inward. If I go here, it's also coming over the loop, it's going inward. Alright? So again, this is equal to the whatever is the change, right? So this is the induced flux, which means seeks the counteraction of the change, which is this induced magnetic field. Alright? Now, how do we represent, how do we include this change in the Faraday's law? So what we do is the following. We have, this is the Faraday's law, E is equal to N, which is the number of turns in the coil, times the change in the magnetic flux with the time, right? Now, I do not have an absolute value over here, but instead I put the negative sign. This negative sign tells me that coming from the Lenz's law, and the Lenz's law says the effect of the cause is opposing the cause. The effect will be opposing the cause, right? So the negative sign, this is the Faraday's law, but the negative sign in the Faraday's law, which indicates the direction of the EMF induced. Okay, whatever is the direction of the cause, opposite will be the direction of the effect, induced EMF. Right? This is told to us by Lenz's law. Now, the Lenz's law, let's refine it and rewrite it, the Lenz's law. So the Lenz's law is simply tells us the polarity of the induced EMF, and it says the polarity of the induced EMF is such that it produces a current whose magnetic field, which means the induced magnetic field, produces a current, induced current, whose magnetic field, which means the induced magnetic field, opposes the change in the magnetic flux. So, as I said in the beginning, it tries to maintain the constant flux, the magnetic field lines through the coil. Alright? Same number of magnetic field lines going through the coil all the time. But it is changing phi, right? So, it will do that because the induced current wants to maintain the magnetic flux through the circuit. Now, this has an implications in several ways. One of them you might have noticed. All of you use the credit cards or ATM cards, whatever you use, as long as you have money in those cards. So when I swipe the card in the machine, so what happens is I am changing the flux. This is a magnetic strip and it's changing the flux. Okay, so by changing the flux, I induce the current. As a result, there is a reader in there which will read all the information and carry this information in the form of the electrical signal and through the bank's tower or a computer. And it will tell that, okay, you have the money, or you are how much money you have, how much money you can take. Alright? So this is one of the implications. And not only that, since most of you are going to be joining the medical field in one form or the other, so we have another important thing called apnea monitor. So this is a coil of wire which is attached to the chest, to the born baby. Usually, mostly of the time, the apnea meter is used for the newly born babies to see this baby is breathing or not. Now, the alternating current. So the direct current is a unidirectional current, but the alternating current is changing, all right? Changing the cycle. This alternating current, it means the current is changing every time. The current is changing in the magnetic field produced by the current through the coil will be changing, right? So now, then this passes through the coil, and while the baby is breathing, so this will be, it will be keep telling the change in flux, right, while the baby is breathing. When the baby breathing stops, the pattern of the induced voltage will be stabilized. Because if the baby is breathing, there will be too much change in the flux, right? So when the change in the flux, the EMF keep changing, right? So as the EMF induced will be keep changing, it means the baby has some problem with the breathing process, yeah? But the breathing, so all the, not the problem with the breathing process, basically the baby is doing good, and then the breathing stops, the pattern of the induced voltage stabilizes, and the external monitors will give us an alert sound, okay, something weird is happening, all right? So that is one of the implications in the medical field. And also there are several the metal detectors. In the metal detectors also there is a magnetic field, right? When you pass through the magnetic field, if you are carrying a metal object, that metal object will interfere with the changing magnetic flux, right? As a result, the signal will be generated, the induced current and the induced voltage, and it will trigger the signal. The signal will be generated in the form of the electric current, induced current, and you will see then it will trigger the people who are watching that, okay? Will give you the red or green signal, okay? Well, the red signal usually when there is a change in the magnetic flux. If there you have nothing metallic in with your body, then there will be no change in the magnetic flux, right? Then your body, it will pass through. Now, there is another important implication, as I said as last time. So, if you go to the traffic signals, just at where you stop on the traffic signal, you will see mostly something like that. So there is a conducting coil over there. When your car passes over that and stop by that, then it's changing the flux. By changing the flux, it will induce the current and it will trigger the traffic light that, okay, there is a car waiting for you to turn green. So the signal will change from there and it will allow you to move. So this is usually done on the different places, but with the latest technology, usually they have the signal timing up to 1 minute or 2 minutes, but in some places still it is being used, and Louisville several places it is being used. All right, now let's talk about the example. The transcranial magnetic simulations, for example, called TMS, is a, for example, a repetitive TMS pulses can treat depression and the mood disorder, also another medical field related example. The magnitude of the magnetic field from a TMS coil increases from 0 Tesla to 0.2 Tesla in 0.002 seconds. The magnetic field lines pass through the scalp into a small region of the brain, inducing a circular current in the conductive brain tissue in the plane perpendicular to the field line. Okay? Now, plane perpendicular to the field line. Assume that the radius of the circular current in the brain area, which is perpendicular to the field line, is 0.003 meters, and the tissues in the circular region have an equivalent resistance of 0.010 ohms. What are the direction and the magnitude of the induced current around the circular region of the brain tissue? So let's see what we can do here. So this is how the picture looks like. So this is the coil. and the magnetic field line are perpendicular over there, and then you see this is the circular area. Now the EMF induced. In order to find the current, what you need, the current, Ohm's law said EMF is equal to I times R. We are given the resistance, but we don't know the induced current, and we need to find the induced current, right? Which is equal to EMF over R, and this EMF is also induced EMF. Now we use, first of all, let's find the induced EMF. So we know from the Faraday's law the induced EMF, now again here is an absolute value, you don't need to worry about the Lenz's law. We know that the negative sign will tell you the direction of the voltage. So here induced EMF, number of turns in the coil is 1. If it's not given, that's 1. Now this is a circular thing. Now final magnetic field times the area, which is the change in the flux, right? Final magnetic field times the area. Area does not change, but the magnetic field change, right? By moving that. So minus the initial magnetic field times the area. So then of course this is multiplied with cosine of the angle. This is multiplied with cosine of the angle. Right, between the normal to the area vector, which is here, and the magnetic field. So let's see. The angle between them is 0, so the cosine theta, cosine of 0 is 1, theta is 0, cosine of 0 is 1, so that is sorted out. Now you are left with this part, area. So area of the circle is given to us, radius is given, this is pi r square. So you can do that. What is changing is the magnetic field, right? So let's see, I sort this out, n number of turns, area remains same, cosine theta remains same. So the magnetic field changing and the time changing. So let's do that. Now n times pi r square, which is the area, cosine of the angle 0. The magnetic field changes from 0 to 0.2 Tesla, which is this, and the time changes from initial 0 to 0.002 seconds. So I'll plug in everything over here. This is 1, n is 1, okay. Then all plugging in the numbers, you get this much voltage. That is the induced EMF. Now, if I use this induced EMF over here, and the resistance is given to me in ohms, then I will get the current. Now, from here, since the magnetic field is coming downward, the induced magnetic field will be upward. So the induced magnetic field will be upward. It has to oppose the cause which produces it. This is the only way it will be upward is the current is going that way, right? So that is the induced current direction. That is why it says counterclockwise. Okay? So this is the only way it can be. This is the external magnetic field, blue lines. Okay? B external. Okay? So these blue lines. Okay? Now, the induced magnetic field has to oppose the cause, and it can only oppose the cause if the current is moving in the counterclockwise direction. Alright? So here is another one. It says a wire loop of radius point that's doing this. A wire loop of radius 0.3 meter lies so that the external magnetic fields of the strength 0.0 plus 0.03 Tesla is perpendicular to the loop. Perpendicular to the loop means the area, normal to the area, the surface area of the loop basically. The field changes to minus 0.02 Tesla in 1.5 seconds. The plus and the minus signs here are referring to the opposite direction of the magnetic field through the loop. Find the magnitude of the average induced EMF in loop. Okay? Now let's go further and see what we can do. So radius is given, initial magnetic field is given, final magnetic field is given, the time going from initial to final is 1.5 seconds. Now I want to find the EMF induced. EMF induced is the change in the flux with respect to time, right? Now what is the change in flux? The change in flux is the final flux minus the initial flux and time. So what is the final flux? The magnetic field is changing, area is not. So it means the change in the flux is equal to phi final minus phi initial, which is B final times area minus B initial times area, and of course the cosine of the theta, since they are perpendicular. So this cosine theta is 0, the cosine of 0 is equal to 1, so that will be gone. Alright, so now I have only what is changing is a loop, circular loop, which is area is pi r squared, right? So now I calculated the initial flux and the final flux without using anything else. See, that will, if I don't do that, it will confuse with the negative sign, because there is a negative sign with the magnetic field as well. So here, initial flux is the initial magnetic field times the area. Cosine of the angle is 0, so which is 1. So initial magnetic field 0.3 Tesla times pi r squared. This is this much. Now after the field changes, the final magnetic field is minus 0.02 Tesla, then pi r squared. This is equal to negative of this. All right. Now the change in flux. All right. So the change in flux is two things. Final minus initial. As I said, the negative and the plus signs only refer to the opposite direction of the magnetic field. So when you are going to add them, so there's opposite direction already. So you change that and plug that in, and you get the EMF 0.0095 volts. But cross check the numbers. All right. So we stop it here.